Okay, show of hands. Who uses the definition of a derivative every time they take a derivative? What? No one? No, seriously. No one does, right? Why is that? Well, it's because the definition of a derivative gets kind of clunky sometimes. Well, the definition of the Laplace transform has had us doing integration by parts over and over again. That's kind of clunky too, right? So, just like derivatives, the Laplace transform has some nice properties that allow us to simplify it some, so that maybe we don't have to integrate by parts for days, all right? So far, we've only been taking the Laplace transform of really simple equations. So you can imagine that as those get more complicated, even if it doesn't feel too bad to you right now, it could get pretty bad. So we're going to use these properties to help us out. So let's talk about the first one of these properties. So the first property is called translation on the s-axis. And just to help motivate you along the way, I'm going to tell you, what if we wanted to take the Laplace transform of e to the t squared sine 3t? That was our function. So if this ever starts feeling too complicated, then just look at that transform that we would want to do and imagine the integration by parts you would have to go through. So putting that horror aside, let's go to our first theorem. It's called the first translation theorem. If the Laplace transform of f of t equals capital of f of s, and a is any real number, then the Laplace transform of e to the at f of t is going to equal capital F of s minus a. Well, that's helpful for us, right? So let's take a look at an example. Say I want to take the Laplace transform of e to the 5t t cubed. What this theorem is saying is I'm really going to be taking the Laplace transform of t cubed. And what I'll be looking at, though, is I'll be replacing s's with s minus a, so in this case s minus 5. Well, the Laplace transform of t cubed is one of my easy ones on my list. That equals 3 factorial divided by s to the 3 plus 1, or s to the 4th. And we're going to be replacing s's with s minus 5. So I'll do my substitution and I'll work out that factorial. 3 factorial is 3 times 2 times 1, which equals 6. And replacing s with s minus 5, I have s minus 5 to the 4th power. And in doing that, I just took the Laplace transform of a product of e to the 5t and t cubed. It would have taken me multiple integration by parts to do that from the definition, but using this first translation theorem, I was able to do it in 3 easy steps, completely simplified. So in order to have this be a useful theorem, useful translation, we also need to be able to do the inverse. Remember, when we solved the differential equation using the Laplace transform, we needed to be able to take the inverse transform as well. So the inverse transform of capital F of s minus a is going to equal the inverse transform of capital F of s, where we're replacing s with s minus a. And that's going to give us e to the at lowercase f of t, where lowercase f of t is the inverse transform of capital F of s. So in order to do this, what we're saying basically is we need to be able to recognize that substitution that occurred of s to s minus a. So looking at my example, I need to be able to look at that and say, all right, the function that's like underlying all of this is something raised to the 4th power. The substitution that's been made is whatever that something was became s minus 5. So my substitution that was made was plugging s minus 5 in for s, and my underlying function is just 6 over s to the 4th. And then I can use previous theorems to find that inverse transform.